organizers for putting this very nice conference together. As Randy said, I'm going to tell you about charge patterns in. Tell you about charge patterns in systems where fermionic and bosonic degrees of freedom, fermionic and bosonic particles are coupled. I'm going to tell you about that in the context of a particular model, Hamiltonian, the Holstein model, and I'll make some connections as I go along with spin patterns in the Hubbard model. I'm going to tell you a bit about Pyro's original picture of the charge density wave, charge ordering in the solid state systems, and how it is linked to Fermi surface nesting. And what we've done that's new here is to generalize the Holstein model to allow for dispersion of the phonons in more general language, one can say, to allow the bosonic particles to hop from site to site on the lattice. I'll turn also to the original Holstein model and tell you about the transition that can occur between a semi-metal and a charge ordering pattern when bosons coupled to fermions with a Dirac spectrum. And I'll conclude by telling you about a new Langevin-based quantum Monte Carlo algorithm that we've been developing, which we think has a lot of promise to allow very general Fermi-Bose systems to be studied numerically. This is work that I've been doing in collaboration with graduate students, Nathaniel, Wei-Ting, Bo, UC, and an undergraduate student who's just joined Emmanuel Gull's group at the University of Michigan, Thomas, and with George and Ziyang, and also we're looking, I won't have time to talk about this, but disorder in these sorts of systems with Hassan Khatami, who's here as well. Now, of course, theorists have a reputation for oversimplifying things, and the canonical joke in that regard is that we study a spherical cow, perhaps in the context of this conference in a vacuum. And in that sense, the Holstein model has a very unfortunate name to emphasize that reputation. But maybe I'll try to convince you that we're studying here somewhat more realistic cows. Like the Hubbard model, the Holstein model has a considerable lineage. In fact, it was introduced a few years prior to the introduction of the Hubbard model, and it was introduced to study how fermions moving in a solid are affected, their mass is changed, and so on, by their contact with bosonic degrees of freedom, boson modes. And although I've been concentrating on charge ordering patterns, there's a lot of beautiful Monte Carlo work on this original Polaron problem, including things that are done by Nikolai's group. Okay, so both the Hubbard and Holstein model share an electron kinetic energy term, which describes the hopping of fermions on a lattice, optical lattice or a nuclear lattice in a solid. And then in the case of the Hubbard model, as you know, the electrons, these fermions, interact with each other with some sort of on-site Coulomb interaction U. The Holstein model is different. There's no interaction directly between the electrons. Rather, the density of fermionic particles interacts with a boson mode, in the case of condensed matter context, a stretching of the nucleus away from its equilibrium position. And then these bosons themselves have a intrinsic kinetic energy as well. And that's in the Holstein model described by a bunch of completely decoupled bosonic harmonic oscillators. And the independence of the harmonic oscillators on different sites of the lattice implies that the bosonic modes are completely dispersionless. Omega is independent of Q. What we'll be doing is to study a system in which that's no longer true. Similarly, the electron-boson coupling in the Holstein model is assumed to be independent of momentum. Now, as I show you some quantum Monte Carlo results, I'll be telling you those in terms of a dimensionless coupling, which is a combination of the electron-phonon coupling, this phonon frequency, and the electronic bandwidth. Okay, so I would like to connect the Holstein model with the Hubbard model. And because I'll be telling you a little bit about quantum Monte Carlo algorithms, I'll first establish that connection within the context of how we study these systems numerically. Often if you look at quantum Monte Carlo at finite temperature, you begin with the partition function, and you proceed by discretizing the inverse temperature beta to write down a path integral for the partition function. You insert complete sets of states, and what that does immediately is convert these bosonic operators into just numbers. The boson kinetic energy couples the bosonic displacements on adjacent imaginary time slices in a way that looks a lot like the square of a velocity. Now, if we ignore this boson kinetic energy, we can look at the combination of the phonon potential energy and the electron-phonon coupling and do a simple completing of the square. And what happens when you do that is the additional term that you get acts as a renormalization of the chemical potential of the fermions in the lattice, but more crucially, what appears is an effective attraction between up and down spin fermions on the same side of the lattice. And so this argument is supposed to convince you that the Holstein Hamiltonian has a very close connection to the attractive Hubbard model, where we can even see a formula for the effective interaction, the square of this electron-phonon coupling divided by the bosonic energies. We can see that connection in a slightly more sophisticated way by looking at the Hubbard model in momentum space. We transform the local Hubbard interaction into momentum, and of course what you get is a process where you have fermions of momentum k and p scattering and exchanging a momentum q. The Holstein model, on the other hand, has no such direct interaction, but instead what can happen is that a fermion coming along can emit a phonon, can interact with a bosonic atom, a bosonic degree of freedom, and in that scattering process change its momentum. Or, alternatively, an electron that's traveling along can interact with the bosons by absorbing a momentum q. And if we tie these two bosonic lines together, we get an expression, a picture of an effective interaction between the fermions, which looks like the square of this boson-fermion coupling times the free propagator of a boson on the lattice. And we know what that looks like. If we examine that expression and we suppress the omega dependence, we look at low energy of the bosonic degrees of freedom, and we set omega q equal to omega naught, we see that this effective interaction takes the exact same form as the completing the square argument I gave you before. And so one can see from this diagrammatic point of view as well that the Holstein model can be viewed to a large extent as a Hubbard model with an effective attractive interaction between the fermions. Okay, well, so what is the basic physics that can arise from that? Well, in the repulsive Hubbard model, of course, U does one thing immediately. It induces the formation of local moments on all of the sites of the lattice. And then to next order in the hopping, to the quadratic order in the hopping, the local antiferromagnetic correlations develop between these local moments, because an arrangement like this, which is locally antiferromagnetic, has a lower energy than parallel spins, which are Pauli blocked. The exact same argument suggests that charge order should arise in the attractive Hubbard model or in the Holstein model. The first thing that the attraction U does is it forms local pairs, but then with a very similar argument to this picture here, it's energetically favorable for paired sites to be adjacent to empty ones, because that allows the fermions to hop from site to site. So you can see that one expects charge density wave order as an analogy with the antiferromagnetic order in a repulsive model. Okay, so we have this picture of antiferromagnetic order in a repulsive model, attractive charge density wave order in a Holstein model or an attractive Hubbard model. And then the crucial question for us in doing quantum Monte Carlo is whether this local order will become long range as we reduce the thermal and quantum fluctuations. Okay, and then I'll also tell you a little bit about whether when you dope this sort of model, you can get to superconducting order. I've emphasized connections between the Hubbard and Holstein models, so I want to say one crucial difference. In 2 dimensions, because you have a continuous symmetry, a Heisenberg universality class, you can get long-range antiferromagnetic order only at t equals 0. Since the charge density wave transition in this Holstein model is breaking a discrete symmetry, we can actually get a bona fide finite temperature phase transition. Now, I mentioned that the Holstein model has this long history, but interestingly, quantitative values for the charge density wave transition temperature have only been obtained very recently. Let me show you how that's done. Okay, so in the case of the fermionic Hubbard model, of course, you look for antiferromagnetic order by looking at the spin-spin correlation functions and evaluating them at an appropriate wave vector pi. In the Holstein model, you look at charge density wave correlation functions, again, evaluated at an appropriate pi wave vector. If you're at high temperatures, these sorts of spin or charge correlation functions will decay exponentially, and the structure factors will be independent of the size of your system. At low temperatures, if long-range order develops, these correlation functions will approach a constant, and the structure factor will grow with the size of the system. So this is our key diagnostic in simulations for inferring the existence of long-range order. So I show here in this inset precisely that sort of analysis. I'm showing the charge structure factor as a function of inverse temperature for different lattice sizes. And at high temperatures here, small inverse temperature beta, these curves coalesce. The correlations are short range. But as you lower the temperature, these curves break away from each other. The structure factor develops a lattice size dependence. And that's a hint that long-range charge order is developing across our lattice. We can get a more accurate handle on that by doing a finite-sized data collapse of these results for different lattice sizes. And from that data collapse, we can infer a transition temperature for this charge density wave change of the Holstein model. Yes. So, I'm sorry, L is the linear lattice size, and then N here is L squared. It's the total lattice size. So N is 144 here for a 12 by 12 lattice. All right. Now, of course, we get charge order at pi for a square lattice for a very powerful reason. On a square lattice, the Fermi surface, this rotated square, has perfect nesting at this wave vector pi, and that really drives order at that particular wave vector. Now, when Peierls and Holstein first talked about the Holstein model, the interaction between bosons and fermions in the lattice, Peierls emphasized that in one-dimensional systems, there's always Fermi surface nesting, no matter, not just at this particular commensurate filling, but at any density. The two momenta values at the Fermi surface are connected by a wave vector to K Fermi. So the fact that you always have Fermi surface nesting in one dimension has a very interesting consequence, which is that if you have a linear chain of phonons, bosons, and fermions, the lowering of the electronic energy will always overwhelm the cost of creating this pattern of stretched bonds, and you always get a charge density wave phase, a lattice dimerization in one dimension. So this was Peierl's famous picture and his famous argument that, put another way, the susceptibility to charge order diverges in one dimension at twice the Fermi wave vector. And that divergence of the susceptibility to order implies that order occurs for even the smallest coupling between the bosons and the fermions. So this picture sort of pervaded the literature for many decades, but as people have studied charge density wave systems more extensively, there's been a realization that actually it's often the case that there's no sign in band structure of any sort of Fermi surface nesting in materials that are very strong charge density wave materials. And that is our motivation for trying to study the Holstein model with some momentum dependence of the electron-boson coupling or the phonon dispersion to see if we can see charge ordering in the absence of Fermi surface nesting. Okay, so I'm going to tell you about simulations we've done where we've put in bosonic dispersion. We've made the bosonic particles have an energy which depends on momentum. That was our first objective. I'll tell you at the end about efforts to put momentum dependence in the coupling instead. But we do this first because at a technical level, such a generalization of the Holstein model is much more easy to implement in our calculational technique determining quantum mechanics. But I will just tell you that if you take a look at the renormalization of the energy of a fermion moving on a lattice due to its coupling to bosonic particles, and you look at either momentum dependence of the coupling between the electrons and the bosons, or momentum dependence of the dispersion, there's actually a very close connection to these two processes. And so one can infer information about both by studying this simpler problem. Okay, so I review here, say again what the conventional Holstein model is: some electron kinetic energy, an electron fermion boson coupling, and then a bosonic part of the Hamiltonian. And we are going to take this bosonic piece of the Hamiltonian, which is completely non-interacting and local. The bosons don't couple from site to site. And we're going to now allow the bosons to see each other on adjacent sites of the lattice. In terms of cold atoms, that corresponds to allowing the bosonic particles to hop from site to site. We'll consider two different types of terms there. In one of them, we couple the displacements on adjacent sites with a positive term. And what that does is it lowers the energy cost for creating a lattice distortion at pi pi. So we expect that to have a trivial effect of increasing the transition temperature to charge density wave order. On the other hand, if we choose the opposite sign, it penalizes the creation of order at pi pi, and we expect that to suppress the charge density wave order. And I'll tell you that if you do that a sufficient amount of such suppression, we get the interesting phenomenon of superconductivity replacing the charge order at commensurate filling. Finally, we can do a mixed type of hopping where we have opposite signs depending on when one travels in the two-dimensional lattice in the horizontal or vertical direction. That will lower the energy cost for the creation of a bosonic mode at 0 pi. That'll create striped charge density wave patterns. Okay, so let me first show you that simplest of effects, namely if we tweak the energy cost for creating a bosonic mode at pi pi, either making it easier or more expensive to create those. Well, if we make it easier to distort the lattice at pi pi, the critical beta goes down, the critical temperature goes up. And likewise, you can see that if you make it more difficult to create a bosonic mode at pi, the system has a lower transition temperature for charge density wave order. So we've sketched out the phase diagram of this coupled Bose-Fermi system as a function of this amount of kinetic energy for the bosonic particles on the lattice. What about this transition between different charge ordering patterns, a checkerboard pattern to a stripe pattern? Well, in order to induce the stripe pattern, we turn on this mixed sort of hopping in the horizontal and vertical directions. And I'll first show you that when we look at the structure factor at momentum 0 pi, we indeed get this growth with lattice size as you decrease the temperature, signaling the formation of a striped charge density wave pattern. And we can calculate in a way that you've seen already the transition temperature for that stripe pattern. And then we can look more closely at the transition between this checkerboard staggered charge density wave pattern that we originally had and this new striped charge density wave pattern that we get by turning on the bosonic dispersion. Okay, so what is the key observation here? I want to emphasize that this Pyros picture, which links charge density wave formation sort of inextricably to the nesting of the Fermi surface wave vector, and sort of underlied our view in the condensed matter community of how charge density waves form. This is a counterexample to that picture. By changing the phonon dispersion, we've made no alteration whatsoever to the underlying electronic band structure. We still have a half-filled square lattice, Fermi surface nesting at pi, but the charge density wave ordering vector can change from pi to 0 pi. So this is a charge density wave transition which is outside of the canonical Pyros picture. Now I've showed you a lot of data repeatedly for the structure factor because that's perhaps the best diagnostic we have for the formation of long-range charge and spin patterns. It's the diagnostic that connects most directly with scattering experiments in cold atoms. But we also can look at the same sort of phenomenon by looking at the plateaus, the Mott or Slater plateaus in the density of particles as a function of the chemical potential in the system. Or we can calculate the density of states and see these sorts of charge gaps develop in that quantity as well. All right, so the additionally interesting thing that I'd like to describe to you is that not only can one have transitions from charge ordering patterns at different wave vectors, but normally our intuition is that when you have commensurate filling, when you have one particle per site, you have a very strong tendency to diagonal order, to AntiFerromagnetic order or charge density wave order. And it's very rare and almost unprecedented to see a superconducting order at such commensurate fillings. But by inhibiting the charge order with the introduction of this hopping of the bosons on the lattice, we can open a window for superconductivity to replace the charge order that's been suppressed.
Just a bit.
Yes.
So the hopping that introduced effectively is changing the momentum dependence of the interaction.
Well, so what it's done most immediately is to give the bosonic particles a momentum dependence to their energy. But I tried to argue with that little picture of the electron self-energy that those two different momentum dependencies in the boson-fermion coupling or in the bosonic dispersion relation are in fact very closely related.
But you need that, otherwise you still have nesting. That's important.
Yes, correct.
Does this boson have to be a lattice phonon, or it could be bosons out of the electronic degrees of freedom?
Oh, good question. We're considering bosonic particles on a lattice, but yes, lots of questions.
So I was wondering if you can actually, if an opposite phenomenon can also occur away from commensurate filling, for weak electron-phonon interaction, you're basically guaranteed to have superconductivity because of BCS instability.
Yes.
But if the electron-phonon interaction becomes too large, and you're not guaranteed that then there is no Migdal theorem, and maybe then you can drive charge density waves even away from commensurate filling just because of large lambda.
Right. That's an interesting thing, and I should say something technical here, which is that, as you all know, we have had this problem in studying Hubbard models that we find it very difficult to build the system because of the sign problem. One of the nice things about these electron-phonon models is that we can go to low temperatures. We have not done that yet and look at the sorts of things you're suggesting.
Maybe a follow-up question. I was wondering for the Hubbard model, if somehow we make the on-site interaction have some momentum dependence in momentum space, will we go back to the model we are talking about?
That could very well happen.
So, that's it.
Yes, I also have a somehow related question about the boson particle. So, you have this formally that is a linear dispersion. So, what happens if you have a different dispersion which is not linear, quadratic momentum, or not zero and zero momentum? So where this dispersion really enter in which sense? So if you look by hand another dispersion that you just embed, whatever, how do you...
Yeah, so there have been some studies of anharmonic bosonic dispersions, and in general they tend to reduce the tendency of charge order and make it more costly to create charge order patterns. So that's probably as much as I know about. More general. Well, okay, I think that in the case of the anharmonicity, it creates an asymmetry between, I didn't emphasize this, I showed pictures of what the fermions were doing on the lattice, this alternation of doubly occupied and empty sites. The phonons, the bosonic particles, are also alternating on the lattice, but when you introduce an anharmonicity, you introduce, it's sort of like a particle asymmetry for the bosonic particles, and I think that's the picture of why charge ordering is less likely in that case.
Okay, that's why I propose that we let Richard finish.
Okay.
And we'll open it up for questions.
So I think I wanted to say here that we look at this charge structure factor as a function of this asymmetry, this phonon dispersion, and it comes down. And we also look at the pair structure factor, and it builds up as we, the enemy of our enemy is our friend. As we kill off charge density wave, we open this window for superconductivity. And it's pretty low temperature, though. The critical temperature is a factor of 4 or 5 lower than the critical temperature for this charge order. So we think we see superconductivity at commensurate filling, but it's certainly less easy to observe. Okay, I will just very quickly tell you about this Holstein Model on the honeycomb lattice. We take a look at this, of course, because there's a lot of interest in fermions with a Dirac spectrum, and there's been a lot of numerical work on what a Hubbard repulsion does, and the fact that there's a quantum critical point. The Hubbard repulsion must exceed a threshold value to convert the fermions into an antiferromagnetic ordering pattern. So we're asking the analogous question here: what happens when we instead put an electron-boson interaction into our system? So I showed you momentum space pictures mostly up till now, but just to for the sake of variety, I'm just going to show you what happens to the charge pattern as you move around on this honeycomb lattice, and as you lower the temperature. And at high temperatures, the charge pattern falls off very rapidly with separation, and as you lower the temperature, these long-range charge correlations build up. That's another way to visualize the charge density waveform. Maybe I'll